I would like to go through a guide that I've found which can help you make quick sense of all the steps that we're going to look at in more detail. And this is a guide from Promega. It's called Molecular Cloning Guide, and it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sections, and it goes through everything you need to know, from sourcing your fragment DNA to ligating it to transforming your host organism to expressing your gene of interest to checking for whether things have gone as you had planned or not. So the reason I've given you this is because it's got good explanations, but also it also has it's got videos which show you how the actual activity would look in the lab. And then it also has the protocol here, so you can actually visualize the kind of reagents you're going to need to actually do this. And there's also this section here, which I want you to do to show that you've understood, or at least had a look at this. There's a little calculation at the very end, which I will show you. So if we start at the top, it's from this company called Promega, which makes a lot of cloning products, and usually they have all this support material which helps you to do the actual activities in the lab. So the beginning is the restriction digest, and if we go there, there's a video which you can look at and see how the restriction endonucleases work, and also really see what a palindrome looks like and the different types of restriction enzymes which are there. We use type 2 restriction enzymes because they completely cleave the DNA. Other restriction enzymes just nick it, meaning that they just cut one of the strands, not both of them, not giving you the actual product you want. And then here is the typical protocol or recipe that you're going to use in order to set up a restriction digest. And if you look carefully at the components, there's nuclease-free water, so you have to have water with no nucleases in it. And when it says nuclease, what it's actually referring to is these same enzymes that we're trying to avoid, the restriction endonucleases. Then we've got your buffer. Then you've got BSA, which is an additive, that's bovine serum albumin. At this concentration, these are additives you add so that the actual reaction will work properly. And then you've got your DNA, so that is your DNA of choice that you actually want to cut. And you would have prepared this DNA by doing a DNA extraction from whatever source, whether it's plant or DNA or animal or microbial. Then you've got your enzyme, and you can see the unit here used for enzyme. That's how many units you're going to have. So pay close attention to this, it will become important later. And then it tells you what the final volume of the whole reaction should be. And you can see that it's in microliters. So this is 20 microliters, which is a very tiny volume. And it means that you can use these really expensive components in tiny amounts to get your result. So once you've set this up, that is what gives you the fragments that you need to put on your gel. So there's all these things to consider: the right temperature, the right combination of enzymes, and then if you're doing a restriction digest with two different enzymes, they might not have the same perfect working conditions. So this is the thinking that has to go into your decision making. And so you can just read that. Here's a bit about double enzyme digest. So how do you set up this same experiment when you're actually doing two restriction enzymes? You remember in the previous exercise, you showed how you could use two different enzymes to cut your DNA. Well, how would you set that up? So instead of just having one enzyme here, you'd have two. That is known as a double digest. And that's what this section is all about. So you can have a read about that. Then you can skip this part about partial digests, because this is for southern blotting and western blotting, mainly southern. So when you're making a library, that's when you do partial digests, meaning you don't actually digest everything to completion. So for now, you should just understand how you set up your digest, which enzymes you're going to use, what conditions, what you need to add in your test tube, or in your Eppendorf tube. And then this bit becomes important when we start looking at hybridization. So there's also a section on creating blunt ends. Remember we talked about blunt and sticky cutters? So this is more about that. And why is it important to actually do this? We'll go into that when we're actually in class. For now, I want you to go on straight to ligation, because you're asking, well, how do you put all these fragments together? So there's a video here about ligation, how you stick your DNA that you've restricted with a different enzyme, how you stick it together with your insert DNA. And then here, there's a little bit more about T4 ligase. And if you've done any molecular biology, you must have heard of Okazaki fragments. So this is the paper where Okazaki discovered those fragments and described how DNA is actually replicated. And so from that technology, we got that and we understood how to actually use it in the lab for cloning. So after you've read that, this is the calculation I would like you to do. So when you do a ligation, you have to understand what's the ratio of insert to vector DNA. This is a very important equation to master because you need to know how much of each that you're going to put in your test tube. And the equation goes like this, where you've got your nanograms of vector times your kilobases of insert over your kilobases of vector. You multiply that by the mole ratio of insert over vector. And that gives you how many nanograms of insert you're going to need. So this sounds quite complicated, but after we've done a bit on gel electrophoresis, I'll show you how you can do this just using your, just looking at the gel. You'll be able to tell what kind of ratios you need. So this is an important step in deciding how to assemble your ligation. And so you can see here a ligation protocol where you've got 100 nanogram of vector, 33 nanogram of insert DNA, then you've got your buffer, and then you've got your enzyme, then you make it up to 10 microliters with nuclease-free water. And you'd leave that for a certain amount of time depending on the enzyme. And you'd, usually you actually leave it overnight, and then you'd be able to check it on gel to see if your ligation has worked. So you can have a look at that, and then, so here you have the timings right there. Then I also want you to look at this gel electrophoresis. So this is a nice video that shows you how the DNA is actually running on the gel and the principles for the separation. Why does the DNA run in one direction, not the other? How do you tell the differences in size? Where do you put your marker? How do you make sense of all that? So this video will give you some background about that. So kindly watch those sections, and then we'll be in a position to start talking about PCR cloning and the strategies that we've been doing in the past few weeks. And then how do you get all of this, once you've got your construct, how do you get it into your bacteria or your plant? And how do you screen for your recombinants? So watch this, then we can start that.